Think of a moment you'd go back to, if you could. Not a grand historical event, not something dramatic, just a moment from your own life. A specific afternoon, a particular conversation, a day that felt ordinary then, but that you'd give a great deal to stand inside again for just a few minutes. Maybe someone you loved who is gone now. Maybe a version of yourself that existed before something changed. Maybe just a Tuesday in a year that felt easier than this one. Maybe a morning when a particular person sat across from you at a table and the light was coming through a window and you were just talking about nothing important and you didn't know it was the last time. Almost everyone has a moment like that. The idea of going back to it, of stepping back into the stream of your own past and standing there again, present and aware and knowing what you know now, is one of the oldest and most persistent human fantasies. We've told stories about it for as long as we've told stories. The desire to undo, to revisit, to correct, to simply be there again. The fantasy is not always about tragedy. Sometimes it's simpler than that. A summer afternoon, when you were 10 years old, before anything complicated had happened yet. A meal with a person you love, before time wore that love into a different shape. A moment of pure, uncomplicated happiness that you didn't fully appreciate while you were in it. The wish to go back is often not the wish to change anything. It's the wish to be present in a way you weren't the first time, to pay proper attention, to know what you were in the middle of while you were in the middle of it. That's what time travel would offer, at its deepest level. Not the ability to fix history, but the ability to truly be in the moments of our own lives that we passed through too quickly, too distracted, too unaware of their significance. The wish to go back is, in some ways, a wish to have been more awake. Almost everyone has a moment like that. The idea of going back to it, of stepping back into the stream of your own past and standing there again, present and aware and knowing what you know now. It's one of the oldest and most persistent human fantasies. We've told stories about it for as long as we've told stories. The desire to undo, to revisit, to correct, to simply be there again. The phrase time machine didn't exist before 1895. Before that year, time travel in fiction happened through magic or dreams or divine intervention. A character might be transported to another era by supernatural means, as in Mark Twain's 1889 novel, A Connecticut Yankee in King Arthur's Court, or might experience a prophetic vision of the future, or travel through time in a dream. But the idea of a machine, a device that could be engineered and operated to travel deliberately through time, was new. It came from Herbert George Wells. H.G. Wells was born in Bromley, Kent, in 1866, the son of a professional cricketer and a housekeeper. His early life was difficult. The family was poor. He worked in a draper's shop as an apprentice, in conditions he later described as miserable. But he managed to win a scholarship to the Normal School of Science in London, where he studied under Thomas Henry Huxley, the great biologist and defender of Darwin's theory of evolution. Huxley's influence on Wells was enormous. It gave him a foundation in scientific thinking that would inform all of his fiction. Wells began writing science fiction in the early 1890s, and in 1895 he published The Time Machine. It was a sensation. The novel tells the story of a Victorian inventor who builds a machine that can travel through time, goes forward to the year 802,701 AD, and finds a world utterly transformed. The Eloi and the Morlocks, the two species humans have evolved into, reflect Wells's anxieties about class division in Victorian England. The time machine itself is a device with levers and dials, controlled by the traveler, moving through time, the way a locomotive moves through space. Wells's genius was to take the concept of time as a fourth dimension, which mathematicians and physicists had been discussing in the late 19th century, and apply it to the possibility of movement. If space has 3 dimensions and you can move through all 3, why couldn't time be a fourth dimension through which you might also move, given the right technology? This imaginative leap established the framework that all subsequent time travel fiction has worked within. What Wells didn't know, writing in 1895, was that within a decade, Einstein would show that time really was a fourth dimension, that space and time were united in a 4-dimensional spacetime, and that the properties of this spacetime were genuinely strange, genuinely different from Newton's absolute time. The physicist's discovery didn't make the novelist's story true, but it made the underlying premise that time is a dimension that might in principle be traversed, scientifically respectable, in a way it hadn't been before. And here is the extraordinary thing. The universe has not simply ignored this fantasy. The universe has its own things to say about time travel. Some of them are stranger than any story we've imagined. Some of them suggest that certain kinds of time travel are not only possible, but are actually happening right now, all around us, enforced by the laws of physics, whether we want it or not. Some of them suggest that traveling into the future is not just possible, but proven, and some of them suggest that traveling into the past raises problems so deep, so tangled in paradox and contradiction, that the universe itself may have mechanisms to prevent it. Tonight, we're going to walk through all of it, slowly, gently. We're going to talk about what time actually is, which is less settled than you might think. We're going to talk about what Einstein's theories say about time travel, and the answers are remarkable. We're going to talk about wormholes and closed time-like curves, and the grandfather paradox, and Novikov's self-consistency principle, and Hawking's chronology protection conjecture. We're going to talk about what quantum mechanics has to say about the past, and why some physicists think the block universe view of time means the past, present, and future all exist simultaneously. If you drift off somewhere along the way, that's perfectly fine. Time will pass regardless. But if you stay with me, I think you'll find that time travel, for all its reputation as pure science fiction, is one of the most seriously discussed topics in theoretical physics, with some of the most brilliant people alive having strong and conflicting opinions about what is and isn't possible. Let's begin. At the beginning, appropriately enough. What is time? It sounds like a question with an obvious answer. Time is what clocks measure. Time is what passes while you're waiting. Time is the sequence of before and after, cause and effect, yesterday and tomorrow. We all have an immediate, intuitive sense of what time is, because we live inside it. We feel it moving. We watch it running away from us when we're having fun, and crawling when we're bored. We remember the past and anticipate the future, and experience the present as a kind of narrow knife edge between the two, always moving forward, never stopping. But ask a physicist what time is, and the answer becomes considerably less obvious. The honest answer is that we don't fully know. Time is one of the deepest and least understood concepts in all of physics. We can measure it with extraordinary precision. We can describe mathematically how it behaves under various conditions. We know how it relates to space, to energy, to gravity. But what time fundamentally is, at the deepest level, is an open question that has occupied physicists and philosophers for centuries without reaching a satisfying resolution. The ancient Greeks had various views on time. Aristotle thought time was the measure of motion, that time was defined by change, that without anything changing, there would be no time. If the universe were perfectly static, Aristotle believed, there would be no time either. Plato distinguished between time and eternity, with time being the moving image of eternity, a less perfect copy of the timeless realm of forms. The Stoics thought time was incorporeal, a kind of framework within which events occurred, not a thing in itself, but a container for things. Heraclitus, perhaps the most poetic of the ancient Greek thinkers about time, said, "You cannot step into the same river twice, because new waters are always flowing. The river changes, you change. The moment is never exactly repeated." His student Cratylus reportedly went further and said, "You cannot step into the same river once, because by the time you've stepped, both you and the river have already changed." Saint Augustine, writing in the 4th and 5th centuries AD, captured the subjective paradox of time beautifully. He said he knew perfectly well what time was, until someone asked him to explain it, at which point he no longer knew. His famous reflection on time in his Confessions is still quoted by philosophers today. He noted that the past exists only as memory, the future only as expectation, and the present is so fleeting that it cannot be said to have any duration at all. The present moment, by the time you try to grasp it, has already become the past. The medieval Islamic philosopher Avicenna, Ibn Sina, working in the 10th and 11th centuries, argued that time was a continuous quantity, that it couldn't be divided into indivisible atoms of time, the way some ancient Greek atomists had proposed. He developed sophisticated arguments about the nature of time's continuity and its relationship to motion that anticipate some aspects of later mathematical treatments. But none of these ancient and medieval views quite captures what modern physics has revealed about the nature of time. The first really important modern insight about time came from Isaac Newton, who built his physics in the late 17th century on what he called absolute time. Newton was explicit about this in the opening pages of his Principia Mathematica, the work that established classical mechanics. He distinguished between mathematical time, which he defined as flowing equably and uniformly without relation to anything external, and relative time, which was the ordinary sensible measure of duration by means of some motion. For Newton, true time flowed uniformly, independently of anything in the universe. Whether or not there was any matter or energy or motion, time ticked on at its absolute rate. It was the stage on which physics played out, unaffected by anything on the stage. It was the same everywhere. It passed at the same rate for everyone. This Newtonian view of time is essentially the common sense view, the one built into our everyday intuitions and into the grammar of every human language. Time is the same for everyone. A second here is a second there. Clocks in different places, moving at different speeds, experiencing different gravitational fields, all tick at the same rate. Of course they do. We have no everyday experience that suggests otherwise. At the speeds and gravitational fields we encounter in ordinary life, the deviations from Newtonian time are so small as to be completely undetectable without sophisticated instruments. But they don't tick at the same rate. And the person who showed they didn't was Albert Einstein, in 2 separate revolutions that we've discussed in our previous conversations. The first was his 1905 special theory of relativity, which showed that time passes at different rates for observers moving at different velocities relative to each other. The second was his 1915 general theory of relativity, which showed that time also passes at different rates in different gravitational fields. Stronger gravity means slower time. These are not small corrections. They are fundamental features of the universe. They have been confirmed by experiment again and again, to extraordinary precision. Time really does pass at different rates, depending on how fast you're moving and how strong the gravitational field is. This is not a metaphor. This is not an approximation. It is a measured, confirmed, physical fact that your phone relies on every time you ask it to tell you where you are, and it is the gateway to time travel. Let me start with the simplest case. The case where time travel into the future is not just possible, but has already happened, is happening right now, and cannot be switched off. But first, let me introduce a way of visualizing time that physicists find essential, and that will help everything else make more sense. It's called a spacetime diagram, or a Minkowski diagram, after Hermann Minkowski, the German mathematician who developed it. Hermann Minkowski was one of Einstein's former mathematics professors, and he recognized the geometric significance of special relativity more clearly than almost anyone else. In 1908, he gave a famous lecture that began with the words, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." He showed that the true arena of physics was not three-dimensional space with time as a separate parameter, but a four-dimensional space-time, in which space and time were unified into a single geometric structure. In a Minkowski space-time diagram, you draw time going upward on the vertical axis, and space going sideways on the horizontal axis. A single point on this diagram represents an event, something happening at a specific place and time. Your location in space-time traces a path called your world line as time passes. If you're sitting still in one place, your world line is a vertical line, going straight upward, moving through time but not through space. If you're moving through space, your world line tilts to the side. The speed of light appears in the diagram as a diagonal line at 45 degrees. This diagonal defines what's called the light cone. Events inside your past light cone are the events that could have sent a signal to you before now. Events inside your future light cone are the events you could send a signal to, starting now. Events outside the light cone are space-like, separated from you. They can neither influence you nor be influenced by you through any signal traveling at or below the speed of light. The light cone is the fundamental causal boundary in space-time. It determines what is in your causal past and what is in your causal future. General relativity can distort space-time so that light cones tilt. Near a massive object or near a rotating black hole, light cones tilt in the direction of the gravitational source, and in certain extreme situations, near a traversable wormhole, light cones can be made to tilt so far that they close up on themselves. A future light cone that curves around and intersects its own past. That's a closed, time-like curve. That's where time travel to the past lives in the mathematics. Thinking in terms of space-time diagrams is enormously helpful for understanding why certain things are possible and others aren't. Special relativity's prohibition on faster-than-light travel is, in this language, the prohibition on world lines that tilt more than 45 degrees from the vertical. Tilt your world line past 45 degrees, and you're going faster than light. And if you can go faster than light, you can, by choosing the right reference frame, be at your destination before you set out, which is time travel to the past. The prohibition on faster-than-light travel and the prohibition on backwards time travel are, in this deeper sense, the same prohibition. Let me start with the simplest case, the case where time travel into the future is not just possible, but has already happened, is happening right now, and cannot be switched off. You are traveling into the future, right now, at the rate of 1 second per second. That's the baseline. But the rate is not the same for everyone, and the deviations from the baseline are real and measurable. To understand this properly, let me take you back to the core insight of special relativity. Einstein showed that the speed of light is the same for all observers, regardless of their motion. And he showed that for this to be true, time cannot pass at the same rate for everyone. If you're moving fast relative to someone who is stationary, your clock runs slower than theirs. This is time dilation, and it's been confirmed in hundreds of experiments. The most vivid demonstration involves particles called muons. Muons are heavy relatives of electrons, produced high in the atmosphere when cosmic rays hit air molecules. They have a natural lifetime, measured in the laboratory, of about 2 microseconds. Given the distances involved, they shouldn't be able to reach the Earth's surface before decaying. But they do. They arrive at the surface in enormous numbers. Why? Because they're traveling at about 99% of the speed of light, and at that speed, their internal clocks run at only about 1/7 the normal rate. Their 2 microseconds, from our perspective, stretches to about 14 microseconds. They live 7 times longer than they should, because time is passing more slowly for them. From the muon's own perspective, it doesn't live any longer. Its internal experience is normal, but the distance it needs to cover, the height of the atmosphere from its frame of reference, has been length contracted by the same factor. The atmosphere appears only about 2 kilometers thick instead of 15. It covers the shorter distance in its normal 2 microseconds. Either way you look at it, from Earth's frame or the muon's frame, the muon reaches the surface. The physics is consistent, and it depends entirely on the fact that time passes more slowly for a fast-moving object. Now scale this up to human beings. The International Space Station orbits Earth at about 28,000 kilometers per hour. The astronauts living on it are moving fast enough relative to Earth that time dilation is significant. An astronaut who spends 6 months on the ISS comes back to Earth having aged about 11 milliseconds less than people who stayed on Earth. 11 milliseconds. Not much, but real and measurable. But if you were to move much faster, the effect becomes dramatic. An astronaut traveling at 90% of the speed of light would age at about half the rate of people on Earth. 1 year of travel for the astronaut would equal about 2 years on Earth. At 99% of the speed of light, the factor is about 7. At 99.9%, it's about 22. The closer you get to the speed of light, the more pronounced the effect. This is genuine time travel into the future, not a metaphor, not a thought experiment that might not apply in reality. Real, physical, tested, measured time travel. The astronaut returns to find that more time has passed on Earth than passed for them. They have, in the most literal sense, traveled into Earth's future. They stepped off the ship a few years older than when they got on, and found the Earth decades or centuries older. This is the twin paradox, which we've touched on in our speed of light conversation. One twin stays on Earth. The other travels on a fast spaceship, turns around, and comes back. The traveling twin is younger upon return. The asymmetry comes from the fact that the traveling twin had to decelerate and turn around, which breaks the symmetry between the two frames. The traveling twin really did age less, not because of some illusion or frame of reference trick, actually, physically, biologically less. Scott Kelly, the American astronaut who spent a full year on the International Space Station, returned to Earth in March 2016. His identical twin brother Mark Kelly, also a retired astronaut and later a United States Senator from Arizona, had stayed on Earth during Scott's mission. The Kelly twins became subjects of the most comprehensive human study of long-duration spaceflight ever conducted. The time difference from Scott's year in space was tiny, about 5 milliseconds, due to the competing effects of velocity time dilation and gravitational time dilation partially canceling each other at ISS altitude. But it was real. Scott Kelly returned to Earth 5 milliseconds younger than he would have been had he stayed on the ground. The twin paradox, demonstrated with actual twins. Now, here's the thing about time travel into the future through relativistic motion. It's one way. You can jump forward in time by traveling fast and then slowing down. But you cannot go back to where you started. When you return to Earth after a fast journey, you find yourself in the future relative to the people who stayed home. But you cannot return to the past. The Earth has moved on, and there is no mechanism in special relativity to undo that. The second form of time dilation, gravitational time dilation, comes from Einstein's general theory of relativity. Strong gravity slows time. A clock near a massive object runs slower than a clock far from it. This is not an intuitive result. It seems backward. You might expect that the furious activity near a massive object, the intense energy, would somehow accelerate clocks, but general relativity says the opposite. Gravity slows time. The reason, if you want a physical intuition, is connected to energy. A photon climbing out of a gravitational well loses energy. Its wavelength increases. Its frequency decreases. This is called gravitational redshift, and it's been measured and confirmed. Now, if the frequency of light from a source deep in a gravitational well appears lower to an observer far away, that means the source appears to be ticking more slowly. The clock deep in the gravitational well appears to run slow, and it's not just an appearance. Time really does pass more slowly near a massive object. This effect is real, and it matters practically. GPS satellites orbit Earth at an altitude of about 20,000 kilometers. At that altitude, Earth's gravity is weaker than at the surface, so time runs faster for the satellites than it does on the ground. The GPS satellites' clocks tick faster than Earth's surface clocks by about 45 microseconds per day due to the weaker gravity. There is also a competing effect from special relativity. The satellites are moving relative to the ground, which slows their clocks by about 7 microseconds per day. The net effect is that satellite clocks run fast by about 38 microseconds per day compared to clocks on the ground. 38 microseconds per day doesn't sound like much, but GPS works by precisely timing radio signals. An error of 38 microseconds per day would accumulate to errors of kilometers in position within a few days. Without relativistic corrections, GPS would be useless within about 2 minutes of operation. The fact that your phone can tell you where you are to within a few meters is, in a real sense, a consequence of Einstein's theories of relativity being correct and being applied in the engineering of the system. At the extreme end, near a black hole, gravitational time dilation becomes enormous. The theory of general relativity predicts that at the event horizon of a black hole, the surface from which nothing can escape, time dilation becomes infinite. An observer hovering just above the event horizon would experience time at an almost infinitely slow rate compared to a distant observer. From the outside, the hovering observer would appear frozen, barely moving, like a film playing at an infinitesimally slow frame rate. If somehow they could survive and return, they would find that enormous time had passed in the outside universe. The movie Interstellar, released in 2014 and produced with the involvement of the physicist Kip Thorne, depicted this effect with reasonable accuracy. The characters land on a planet orbiting close to a supermassive black hole, and due to the extreme gravitational time dilation, 1 hour on the planet corresponds to 7 years back on Earth. When they return to their ship, their colleague has aged 7 years, while they've aged only 1 hour. This is a scientifically plausible scenario, not mere science fiction invention. The numbers in the movie are exaggerated beyond what any real planet could sustain, but the physical principle is correct. The gravitational time dilation near a realistic black hole, though extreme, would require you to be extremely close to the event horizon to produce large effects. The danger from tidal forces, the differential gravity that would stretch you like spaghetti if you got too close, is real and fatal long before you could achieve dramatic time dilation. But for a supermassive black hole, with a mass of millions or billions of times the sun's mass, the tidal forces at the event horizon are actually quite gentle. The event horizon is simply so large that the gradient of gravity across the size of a person is not extreme. For a supermassive black hole, you might cross the event horizon without even noticing, the tidal forces being mild enough to survive, and experience extreme time dilation in the process. You just couldn't come back. The point is that the physics of gravitational time dilation is real, confirmed, and at the extreme end allows for genuinely dramatic differences in the passage of time for observers in different gravitational environments. This is real time travel into the future, driven by gravity rather than velocity. Kip Thorne is worth knowing about, because he is one of the most important figures in the physics of time travel. He was born in Logan, Utah in 1940, the son of an agronomist and a biochemist. He showed exceptional mathematical ability from childhood and was offered a place at Caltech at the age of 17. He studied there under Richard Feynman, who was one of the most brilliant and iconoclastic physicists of the 20th century, and whose influence on Thorne was profound. Feynman taught him to question everything, to seek the deepest understanding rather than just the standard presentation, and to distrust any explanation that he couldn't derive himself from first principles. Thorne then went to Princeton for his PhD under John Wheeler, who had coined the term black hole, and who was perhaps the deepest and most philosophical thinker about space and time of his generation. Wheeler encouraged his students to think about the most fundamental questions about the nature of spacetime, the nature of quantum mechanics, the relationship between information and reality. He famously urged them to follow the physics wherever it led, even to conclusions that seemed absurd or impossible. Under Wheeler's guidance, Thorne began thinking seriously about the extremes of what general relativity permitted. His contributions to gravitational wave physics were enormous, and he shared the Nobel Prize in Physics in 2017 for his central role in the detection of gravitational waves by LIGO. But his work on the theoretical aspects of time travel, particularly through wormholes, has been just as significant for the theoretical understanding of what general relativity permits and what it forbids. In 1985, Carl Sagan, who was writing his novel Contact about a physicist who travels through a wormhole to meet extraterrestrial intelligence, called Thorne to ask whether his fictional portal was physically plausible. Could a wormhole exist? Could it be traversable? Sagan wanted the physics to be as accurate as possible. Thorne took the question seriously, as he took all such questions. He convened his graduate students and set them to work. What they found, and what Thorne, Morris, and Yurtsever published in 1988 in a paper in the journal Physical Review Letters, was that general relativity did allow for traversable wormholes, at least in principle. The paper was remarkable for its honesty and its breadth. It didn't just say whether wormholes were possible. It worked out in detail what the exotic matter supporting the wormhole would need to be like, what the constraints on the wormhole's geometry were, how a traveler would experience the passage through it, and, crucially, how a wormhole could be turned into a time machine. The paper was received with a mixture of fascination and skepticism. Some physicists felt that working out the details of traversable wormholes was frivolous, since there was no evidence they existed and theoretical reasons to think they couldn't be constructed. Others felt it was exactly the right approach. If you want to understand what the laws of physics allow, you should push them to their logical extremes and see what falls out. Thorne's approach was firmly in the second camp. Let me explain how this works, because it's one of the most beautiful and strange ideas in all of theoretical physics. A wormhole is a hypothetical tunnel through spacetime, connecting two distant points by a path that is much shorter than the path through ordinary space. The idea goes back to Einstein and Nathan Rosen, who showed in 1935 that the equations of general relativity admitted solutions that looked like bridges between two regions of spacetime. These are called Einstein-Rosen bridges, or wormholes, a term coined later by John Wheeler. Einstein-Rosen bridges, as originally derived, are not traversable. They're unstable and pinch off too quickly for anything to pass through. But in the 1980s, various physicists, including Thorne, showed that with the right exotic matter with negative energy density, a wormhole could in principle be held open and stabilized. Whether exotic matter with negative energy can exist in the required quantities is an open question, but quantum mechanics does allow for small amounts of negative energy density in certain configurations, through effects like the Casimir effect that we mentioned in the antimatter conversation. Now, here's how a wormhole becomes a time machine. Suppose you build a traversable wormhole with two mouths. Call them mouth A and mouth B. Initially, both mouths are in the same location, and time is synchronized through the wormhole. Now you take mouth B and accelerate it to near the speed of light, take it on a fast journey, and bring it back. Because of time dilation, mouth B has aged less than mouth A during the journey. If you look through the wormhole, you see not just through space, but through time as well. Mouth B is in the same present moment as mouth A, but the clocks through the wormhole are out of sync by however much time dilation accumulated during the journey. If you enter through mouth A, you come out through mouth B at an earlier time. You've traveled backward in time. You've traveled back by the amount of time dilation that accumulated during mouth B's relativistic journey. This is not science fiction. This is what general relativity, taken seriously, appears to permit. Whether it can actually be realized in practice depends on whether exotic matter exists in the required form, and on other questions about quantum gravity that we don't yet have answers to. But the theoretical possibility is there. Now, time travel into the past immediately raises a problem that everyone who has ever thought about it has encountered: the grandfather paradox. Suppose you travel back in time to before your grandfather met your grandmother. You prevent the meeting. Your grandfather never has children. Your parent is never born. You are never born. But if you were never born, you couldn't have gone back in time to prevent the meeting. So your grandfather meets your grandmother, your parent is born, you are born, and you go back in time and prevent the meeting, and so on. The paradox loops endlessly. This paradox seems to suggest that time travel to the past is impossible. Any closed causal loop, Any chain of events that circles back on itself creates contradictions that the laws of physics cannot allow. But the paradox is actually less clear-cut than it first appears. Let me show you why. First, note that the grandfather paradox is a specific scenario, not a proof that time travel is impossible. It says that if you go back in time and make a specific change, a contradiction arises. But it doesn't prove you would be able to make that change. Maybe something would always prevent you. Maybe you'd arrive at the wrong time. Maybe you'd be invisible to the people there, or unable to interact with physical objects from the past. The paradox shows that certain actions would be contradictory, but it doesn't show that time travel itself is contradictory. Second, the paradox assumes a particular model of causality, one where effects reliably follow causes in a single, linear timeline. This is our everyday experience, but general relativity doesn't necessarily preserve this kind of causality in the presence of closed time-like curves. The causal structure of spacetime near a wormhole is different from the causal structure of everyday life, and the rules that apply in everyday experience may not straightforwardly extend to the exotic spacetimes of time machines. Third, and most importantly, the paradox has several proposed resolutions, each of which takes a different view of what would happen in a universe that allowed time travel. Physicists have proposed several responses to the grandfather paradox. The first, and perhaps the most satisfying, is the Novikov self-consistency principle, proposed by the Russian physicist Igor Novikov in the 1980s and 1990s. Igor Novikov was a Soviet and later Russian astrophysicist, born in Moscow in 1935, who made major contributions to the theory of black holes and to relativistic cosmology. He worked closely with Yakov Zeldovich, one of the greatest Soviet physicists, who was also one of the key figures in the development of the Soviet thermonuclear bomb program, and who later turned his attention to cosmology and astrophysics with remarkable results. Zeldovich was one of the first to predict the cosmic microwave background independently of the Western scientists who discovered it, and his work on dark matter, neutron stars, and galaxy formation was foundational. Novikov built on this tradition, developing detailed theories of how black holes would be detected observationally and how the extreme spacetimes of general relativity would behave. Novikov's self-consistency principle says this: any time travel that occurs must be self-consistent. The past cannot be changed, because the past has already happened. If you go back in time and try to prevent your grandfather from meeting your grandmother, something will stop you. Not because of some mysterious force, but because of logical necessity. The events of the past are fixed. They cannot be altered. You can participate in the past. You can even be a cause of past events, but you cannot make the past different from what it was. In this picture, if you traveled back in time to your grandfather's era, you might go to the place where he was supposed to meet your grandmother, intending to prevent it, but something would happen. Maybe you'd trip. Maybe you'd get the date wrong. Maybe you'd accidentally be the one who introduced them, becoming the cause of the very meeting you were trying to prevent. The timeline has a way of maintaining its consistency. Your attempt to change it would always, necessarily, fail or backfire, because the past is what it is, and you already failed when you tried. There's a beautiful and strange implication of this. If you went back in time to meet your own grandfather before he met your grandmother, you would already have been there, in the historical record, even if no one noticed you or recorded your presence. Every person who has ever lived in the past was already surrounded by time travelers who came to visit and who, by the self-consistency principle, had no effect on anything that wasn't already recorded. The past is full of our future selves, invisible and ineffectual, constrained by the logic of consistency. This is the self-consistency principle. Only self-consistent time loops are allowed. If you go back in time, you go back into a past that already contains your visit. You might interact with the past, but you cannot make it different from what it was when you came from. The universe enforces its own consistency. Novikov's principle is mathematically elegant. It resolves the paradox by fiat, by declaring that paradox-creating causal loops are simply not permitted. But it's also philosophically troubling, because it seems to imply that free will is severely constrained when time travel is involved. If you are destined to fail in your attempt to change the past, in what sense are you freely choosing to try? The self-consistency principle seems to require a kind of cosmic constraint on behavior, a guarantee that certain things will always go wrong. One of the most compelling fictional explorations of the self-consistency principle is the story of the woman who traveled back in time and accidentally taught Bach to play music, only to discover that Bach learned to play from her, and she learned from his music that she'd brought from the future, and the music had no origin at all. It existed because it existed. It was its own cause. These self-creating loops, called bootstrap paradoxes or ontological paradoxes, are a feature of self-consistent time travel, and they're one of the most mind-bending implications. Information or objects can exist in a time loop without any external origin, owing their existence purely to the loop itself. An alternative approach is the multiple timelines picture, most famously associated with the many worlds interpretation of quantum mechanics. In this view, when you travel to the past, you don't change the past of your own timeline. Instead, you branch off into a new timeline, a parallel universe that diverges from your own at the point you arrived. In the new timeline, you can do whatever you want, including prevent your grandfather from meeting your grandmother. In that timeline, you are indeed never born. But you weren't born in that timeline to begin with. The you who traveled back came from a different timeline entirely. This picture avoids the paradox by introducing multiple timelines, each one a self-consistent history. But it raises its own problems. What exactly triggers the creation of a new timeline? How do you return to your own timeline if the one you've traveled to is different? The multiple timelines picture is internally consistent, but it's highly speculative and has no direct observational support. A third approach was proposed by the physicist David Deutsch, whose work on quantum computation we mentioned briefly in our antimatter conversation. Deutsch applied quantum mechanics to the problem of time travel and showed that in the quantum many-worlds picture, closed time-like curves, the technical term for time travel loops, could exist without paradox. The key is that in quantum mechanics, the state of a system is described by a wave function that gives probabilities for different outcomes. When you impose the self-consistency condition on a quantum system traversing a closed time-like curve, you get a unique, consistent solution. The grandfather paradox doesn't arise because the quantum states adjust themselves to be consistent. Deutsch's analysis is technically sophisticated and not universally accepted, but it suggests that quantum mechanics may actually smooth out the paradoxes of classical time travel. Some physicists have extended this work in various directions, trying to understand what quantum time travel would actually look like in practice, and what kinds of computations could be performed using closed time-like curves if they existed. The most important practical constraint on time travel comes from Stephen Hawking, who proposed in 1992 what he called the chronology protection conjecture. Hawking argued that the laws of physics conspire to prevent the formation of closed time-like curves, to prevent time travel to the past at the macroscopic level. The conjecture is based on the observation that when you try to build a time machine by distorting spacetime, quantum vacuum fluctuations, the virtual particles that constantly pop in and out of existence in empty space get amplified near the closed time-like curve and build up to infinite energy, destroying the time machine before it can operate. Stephen Hawking needs almost no introduction, but let me say something about him that goes beyond the famous voice and the wheelchair, because his intellectual contributions deserve to be understood as the work of a specific and extraordinary human mind, not as the output of an inspirational symbol. Hawking was born in Oxford in 1942, on January 8th, exactly 300 years after the death of Galileo, a coincidence he mentioned with pleasure in interviews. He grew up in a household full of books, read voraciously as a child, showed a gift for mathematics and physics, and won a place at University College Oxford to study physics. He was, by his own account, not a particularly diligent student at Oxford, where the culture discouraged excessive effort as unfashionable, and he calculated that he was spending on average about 1 hour per day on academic work. He was, nevertheless, brilliant enough that this was sufficient to win him a place at Cambridge for graduate work on cosmology. It was at Cambridge in 1963 that he was diagnosed with amyotrophic lateral sclerosis, ALS, a progressive neurodegenerative disease that would gradually paralyze him over the subsequent decades. He was 21 years old. The doctors told him he had perhaps 2 years to live. He lived 55 more years. He died in 2018, at the age of 76. During those 55 years, working with increasingly limited physical capacity, eventually unable to speak and communicating through a synthesizer, able to move only the muscles of one cheek, Hawking made fundamental contributions to our understanding of black holes, quantum mechanics, and cosmology. His most celebrated result, Hawking radiation, the prediction that black holes slowly evaporate by emitting thermal radiation due to quantum effects, is one of the most important theoretical discoveries in the history of physics, connecting general relativity, quantum mechanics, and thermodynamics in a single result. His 1988 book, A Brief History of Time, became one of the best-selling science books ever written, staying on the Sunday Times bestseller list in Britain for an extraordinary 237 weeks. It introduced millions of people to the ideas of black holes, the Big Bang, and the nature of time. Hawking wrote it in the conscious hope of making physics accessible to ordinary people, and he succeeded beyond anyone's expectations. Hawking held the chronology protection conjecture firmly for many years. He was characteristically bold about it. In 2009, he even held a party for time travelers. He sent out invitations after the party had already occurred, reasoning that if time travel to the past were possible, someone from the future might receive the invitations and come back. He waited. No one arrived. He took this as evidence for the conjecture. The party gambit was, of course, not a scientific proof. Many obvious objections apply. No one from the future might have found or kept the invitation. No one from the future might have been able to travel to that precise moment. Time travel, if it exists, might be subject to constraints that would prevent traveling to moments before the time machine was built. But the gesture captures something about Hawking's personality. He was willing to test ideas playfully, to be wrong publicly, to use unconventional methods to make points about physics. He later relaxed his position somewhat, acknowledging that a complete theory of quantum gravity would be needed to settle the question definitively. The chronology protection conjecture, he said, was a conjecture, not a proven theorem, and until quantum gravity is fully understood, it cannot be elevated to a theorem. The chronology protection conjecture is still not proven. It remains a conjecture. There are physicists who believe it is true, and physicists who believe it may be wrong. Without a complete theory of quantum gravity, we cannot settle the question with certainty. But the evidence from semi-classical calculations, combining aspects of general relativity and quantum mechanics in approximate ways, does seem to support Hawking's intuition. Time machines seem to be inherently unstable. The universe seems not to want them. Let me now tell you about something different. Something that might sound less dramatic than wormholes and grandfather paradoxes, but that is in many ways more philosophically profound. The question of whether the past, present, and future all exist simultaneously. In everyday life, we experience time as a flow. The past is gone. The present is now. The future hasn't happened yet. This seems utterly obvious. It's built into the grammar of every human language, into the way we think about memory and anticipation, into the structure of human desire and regret. We remember the past because it has happened. We anticipate the future because it hasn't. The present is where we live, and it is always moving forward. But in the physics of special relativity, this picture becomes much more complicated. Let me try to show you why. Suppose you're on Earth, and a spaceship is traveling past you very fast, moving toward the Andromeda Galaxy. You and the pilot of the spaceship happen to be at the same location in space at the same moment, which we'll call now. You each look at Andromeda and wonder, what is happening in Andromeda right now? Your answer, and the pilot's answer, will be different. Because of the relativity of simultaneity, because there is no absolute now shared by all observers, what counts as now in Andromeda depends on your state of motion. For you, standing still on Earth, a particular set of events in Andromeda counts as happening simultaneously with your present moment. For the pilot, moving fast relative to you, a different set of events in Andromeda counts as simultaneous with her present moment. The difference is not small. Andromeda is about 2.5 million light-years away. At relativistic speeds, the shift in simultaneity over that distance can amount to thousands of years. What you call now in Andromeda and what the pilot calls now in Andromeda can differ by thousands of years, even though you're both at the same location at the same moment. This means there's no unique, universal now. Different observers, moving at different velocities, disagree about which events in distant parts of the universe are happening now. If there's no universal now, the idea of the present moment as a global property of the universe becomes very hard to defend. The present is local, personal, dependent on your state of motion. It is not a cosmic feature. Some physicists have concluded from this that all moments in time are equally real. The past and the future are not just memories or anticipations. They are as real as the present. They exist. Time does not flow. We simply experience a progression through a four-dimensional block of spacetime in which all events, past, present, and future, are equally, simultaneously present. This is called the block universe view of time, sometimes called eternalism. In the block universe, what we call the past is simply a region of the block that our world lines have already traversed. What we call the future is a region our world lines haven't reached yet, but both regions are equally real. The block is static, four-dimensional, with every event at its proper location in spacetime. Nothing is born and nothing dies in the sense of ceasing to exist. Every event always exists, permanently, at its location in the block. The philosopher J.M.E. McTaggart made a famous distinction in 1908 between two ways of describing time, which he called the A series and the B series. The A series describes events as past, present, or future, positions that change over time. An event that is in the future now becomes present and then past. The A series captures the dynamic, flowing character of time. The B series describes events as earlier than, simultaneous with, or later than each other, fixed relations that never change. The Battle of Waterloo is always earlier than the First World War. These B relations are permanent features of the four-dimensional block. The block universe eliminates the A series. In the block universe, there is no objective distinction between past, present, and future. There is only the B series, the fixed network of earlier than and later than relations. The feeling that events move from future to present to past is a subjective feature of conscious experience, not an objective feature of the universe. McTaggart himself used this analysis to argue that time was not real. His argument was that genuine time requires the A series, that something must really be past and then present and then future, and that the A series is incoherent because every event must be all three, past, present, and future, in sequence. He concluded that time was an illusion. Very few philosophers follow McTaggart all the way to the conclusion that time is an illusion. But the distinction between the A series and the B series has been enormously influential, and the debate between A theorists, who think time really flows, and B theorists, who think the block universe is correct, is one of the most active in the philosophy of physics. Most physicists, when pressed, probably lean toward some version of the block universe view because it's most consistent with the mathematics of relativity. But many are uncomfortable with the full implications and prefer not to think too hard about it. The experience of time flowing, of a present moment moving into the future, is so vivid, so fundamental to conscious experience, that explaining it away as a mere perspective seems to leave something important unexplained. Some physicists, particularly those working on quantum gravity and the foundations of time, take a different view. Lee Smolin, the theoretical physicist at the Perimeter Institute in Canada, has argued in his book Time Reborn that time is fundamentally real, that the present moment is genuinely special, and that the block universe view is a mistake. He argues that the laws of nature themselves evolve over time, that the future is genuinely open and undetermined, and that physics needs to take the reality of time seriously rather than treating it as a mere dimension of spacetime. Smolin's argument, which he developed further with the philosopher Roberto Mangabeira Unger in a book called The Singular Universe and the Reality of Time, is that the block universe is a confusion arising from treating mathematical models as more fundamental than physical reality. The equations of relativity describe the structure of spacetime as a four-dimensional block, but that doesn't mean the block exists in the same way as physical events. The map is not the territory. The equations describe something real, but the block itself may be a feature of the description rather than a feature of what's described. Carlo Rovelli, the Italian physicist and philosopher who has written beautifully about the nature of time, takes yet another view. In his book The Order of Time, Rovelli argues that our common-sense intuition of time as a uniform flow is an illusion built up from our scale of observation. At the fundamental level, he argues, there is no time. The equations of quantum gravity don't contain time as a fundamental variable. What we experience as time is an emergent phenomenon arising from the thermodynamic structure of the world, from the increase of entropy that defines a direction from past to future. This is a remarkable suggestion. Time, in Rovelli's view, is not fundamental. It is emergent, like temperature or pressure, a macroscopic phenomenon that arises from something more fundamental that has no time in it. And the direction of time, the arrow that runs from past to future, is a consequence of entropy, of the fact that the early universe was in a very low entropy state, and entropy has been increasing ever since. The debate between these views, the block universe, the growing block, presentism, the emergent time view, and others, is one of the most active in the philosophy and physics of time. It hasn't been resolved. The nature of time is genuinely one of the open questions at the frontier of human understanding. The arrow of time is a genuine puzzle. The fundamental laws of physics are, with one tiny exception, reversible in time. If you filmed a collision of two billiard balls and played the film backward, the backward film would look perfectly legal. The physical laws governing the balls don't distinguish between forward and backward time. If you filmed a gas expanding to fill a container and played the film backward, the backward film, with the gas spontaneously contracting into one corner, would look impossible. What's the difference? The difference is entropy. The billiard ball collision doesn't significantly change entropy. The gas expansion increases entropy enormously, and the direction in which entropy increases defines the direction of time's arrow. The connection between entropy and time was worked out in the 19th century by the Austrian physicist Ludwig Boltzmann, one of the most brilliant and tragic figures in the history of science. Boltzmann was born in Vienna in 1844, on the night of Mardi Gras, which he always said explained his passionate temperament. He studied physics in Vienna and became one of the founders of statistical mechanics, the branch of physics that explains the macroscopic properties of matter, like temperature and pressure, in terms of the microscopic behavior of atoms and molecules. His central contribution was the statistical interpretation of entropy. Entropy, which had been introduced as a mathematical quantity in thermodynamics by Rudolf Clausius, was mysterious in origin. Boltzmann showed that entropy was a measure of disorder, or more precisely, a measure of the number of microscopic arrangements of the atoms in a system that would produce the same macroscopic appearance. A highly ordered state, like all the gas molecules in one corner, has very few microscopic arrangements that look that way. A disordered state, like the gas spread throughout the container, has enormously many. Entropy quantifies this multiplicity. The natural tendency of systems toward higher entropy is a consequence of probability. There are simply many more high entropy states than low entropy states, so random motion tends to push systems toward higher entropy. There is a beautiful way to visualize this. Imagine a deck of 52 playing cards, perfectly sorted by suit and number. The probability of randomly shuffling them into that exact sorted order is 1 in about 8 times 10 to the 67th power, an incomprehensibly small probability. If you shuffled the deck once per second, you would expect to wait far longer than the current age of the universe before seeing the sorted order appear by chance. The sorted deck is the low entropy state. Every possible shuffled ordering is a higher entropy state. There are almost infinitely many shuffled orderings and only one sorted ordering. Entropy increases because there are overwhelmingly many more ways to be disordered than ordered. This is the second law of thermodynamics at its core. It is not a fundamental law decreed by nature. It is a consequence of probability and the vast number of available microscopic states. The past had lower entropy than the present, not because some law of physics demanded it, but because the initial conditions of the universe happen to be extraordinarily low entropy, and the universe has been evolving toward higher entropy states ever since. This statistical view of entropy was profound. It meant that the second law of thermodynamics, the law that entropy tends to increase, was not an absolute law, but a statistical one. In principle, a gas could spontaneously contract into one corner, just as all the molecules could, purely by chance, happen to be moving in the right directions. It was just enormously unlikely. The probability was so small for a macroscopic amount of gas that it would never be expected to happen in the entire history of the observable universe. But Boltzmann's ideas were fiercely resisted. Many leading physicists of his era didn't believe in atoms. The atomic hypothesis was controversial. Ernst Mach, the influential Austrian physicist and philosopher, was particularly adamant that atoms were a convenient fiction with no physical reality. He and others attacked Boltzmann's work and his interpretations. Boltzmann suffered from depression, possibly bipolar disorder. The sustained attacks on his work and the sense that his deepest insights were not being accepted took a heavy toll. In 1906, while on holiday in Duino near Trieste with his wife and daughter, he hanged himself. He was 62 years old. He died just as the tide was turning in his favor. Einstein's 1905 paper on Brownian motion, the same year Boltzmann died, provided strong evidence for the reality of atoms, and within a few years the atomic hypothesis was accepted by essentially all physicists. Boltzmann's grave in Vienna bears the equation S equals K log W, where S is entropy, K is Boltzmann's constant, named after him, and W is the number of microscopic states corresponding to a macroscopic configuration. It is one of the most profound equations in all of physics, and it is the foundation of the statistical explanation of the arrow of time. The direction of time is the direction of increasing entropy. The past has lower entropy. The future has higher entropy. This is why we remember the past and not the future, why causes precede effects, why broken eggs don't spontaneously reassemble, why we age and don't get younger. All of these asymmetries trace back to the fact that the early universe was in a state of extraordinarily low entropy, a smooth, hot, dense state after the Big Bang, in which matter was distributed nearly uniformly. As the universe has expanded and structure has formed, stars, galaxies, black holes, life, entropy has increased overall. The mystery of why the early universe was in such a low entropy state is connected to the deepest questions about the origin of time's arrow. If the laws of physics are time-symmetric, the early universe didn't have to be low entropy. It could have started in a high entropy state, in which case there would be no arrow of time and no way for complex structures to form. The fact that it started low entropy is connected to the initial conditions of the universe, which physics doesn't yet fully explain. The one exception to time reversal symmetry in fundamental physics is an interaction in particle physics involving certain mesons, the CP violation that we discussed at length in our antimatter conversation. The violation is tiny, and its role in determining the direction of time is not fully understood. It may be connected to the matter-antimatter asymmetry of the universe, but the details are still worked out. So the arrow of time, the reason we experience time as flowing from past to future, and not the reverse, is a thermodynamic phenomenon rooted in the low entropy initial conditions of the universe. It is not a fundamental feature of the microscopic laws of physics, which are mostly time-symmetric. It is an emergent feature of the universe's history. This has a strange implication for time travel. If you could reverse entropy for yourself and your immediate surroundings, you would be traveling backward in time from everyone else's perspective. Your memories would form in what they call the future. You would experience events in reverse order from their experience. But from your perspective, everything would seem forward in time, because your experience of before and after would also be reversed. This is not practically achievable, but it illustrates the deep connection between thermodynamics and the direction of time. Let me also say something about what quantum mechanics adds to the picture of time. Quantum mechanics is the theory governing the behavior of matter and energy at the smallest scales, and its relationship to time is peculiar in ways that are not fully understood. In classical physics, including special and general relativity, time is a continuous parameter that flows smoothly, slowing or speeding, depending on velocity and gravity, but always continuous and always well-defined. You can always say what time it is, at least locally. In quantum mechanics, the situation is stranger. The Schrödinger equation, the fundamental equation governing how quantum states evolve, has time as a parameter, but it treats time differently from space. In quantum field theory, time and space are treated more symmetrically, but there's still an asymmetry. And in canonical quantum gravity, the Wheeler-DeWitt equation, which attempts to describe quantum gravity, doesn't contain time at all as a variable. It's a timeless equation. The universe, in this description, doesn't evolve. It just is. The timelessness of quantum gravity is one of the deepest puzzles in the foundations of physics. Carlo Rovelli's view that time is emergent from something timeless is connected to this. If the fundamental equations of quantum gravity have no time in them, then time must be a feature that emerges at some level, perhaps at the thermodynamic level, when quantum gravity connects to quantum mechanics and statistical mechanics. In that case, the arrow of time would be built into the emergence process, not into the fundamental laws. Quantum mechanics also has something to say about the measurement problem, which is connected to time. In quantum mechanics, a system exists in a superposition of multiple states until it is measured, at which point it collapses into one definite state. But when exactly does the collapse happen? The collapse is instantaneous, or at least effectively so, which seems to conflict with the smooth, continuous evolution of time in relativity. The measurement problem, the question of exactly when and how quantum superpositions collapse into definite outcomes, is one of the most contentious foundational issues in physics. Some interpretations of quantum mechanics, particularly the many worlds interpretation, eliminate collapse entirely. Instead of the wave function collapsing to one outcome, all outcomes happen simultaneously in different branches of the wave function. The universe constantly splits into multiple branches, each containing a different outcome of each quantum measurement. In this picture, time travel to the past might mean arriving in a different branch, as we discussed with the grandfather paradox. And the measurement problem dissolves because there is no collapse, only branching. In the pilot wave interpretation, originally due to Louis de Broglie and later developed by David Bohm, the wave function guides particles along definite trajectories. The particles have definite positions at all times. This interpretation restores a kind of classical determinism to quantum mechanics, while still reproducing all of quantum mechanics' experimental predictions. Time, in this picture, is more straightforward than in other interpretations. The deep question of what quantum mechanics is actually saying about the nature of reality, and specifically about the nature of time, is not settled. Different interpretations of quantum mechanics give different pictures of time. The Copenhagen interpretation, the most commonly taught, is largely silent on the deeper nature of time. The many worlds interpretation suggests a branching structure of time. The pilot wave interpretation suggests a more classical underlying time structure. And the relational interpretation, developed by Rovelli himself, says that time arises from the relationships between physical systems rather than being an independent container. What all of these interpretations agree on is the experimental predictions. Quantum mechanics is extraordinarily accurate. Its predictions match experiments with more precision than any other physical theory. But what those predictions tell us about the fundamental nature of time and whether time travel would be compatible with quantum mechanics depends on which interpretation you adopt. The general lesson is this: quantum mechanics adds layers of complexity and uncertainty to the question of time travel. It may smooth out the paradoxes of classical time travel, as Deutsch's analysis suggests. It may prevent the formation of time machines, as the chronology protection conjecture suggests when quantum vacuum fluctuations are taken into account. Or it may point toward a deeper view of time, in which the question of time travel doesn't even make sense in the usual formulation. We genuinely don't know. Let me also tell you about something that sounds like time travel, but is a more modest and real phenomenon: the way that memories and records of the past persist. In a real sense, the past leaves traces in the present. The universe has a memory. It keeps records. Every physical process leaves effects that encode information about what happened before. Your memory is a record of your past. A photograph is a record of a moment. A fossil is a record of an ancient organism. A geological stratum is a record of a period in Earth's history. The cosmic microwave background is a record of the universe when it was 400,000 years old. Gravitational waves from a neutron star merger carry the record of that event billions of light years across space and billions of years through time. But before we get to that, let me tell you about some other ways that physics allows time travel to the past, beyond traversable wormholes. General relativity admits other exotic spacetimes that may allow time travel. The most physically relevant is the Kerr solution, discovered by the New Zealand mathematician Roy Kerr in 1963. The Kerr solution describes the spacetime geometry around a rotating black hole. It turns out that the spacetime inside the event horizon of a rotating black hole is dramatically different from the spacetime inside a non-rotating black hole. In a non-rotating black hole, the singularity at the center is a spatial entity, a surface of infinite density that anything entering the black hole must hit. There is no way around it. The future inside the event horizon of a non-rotating black hole leads inevitably to the singularity. But in a rotating black hole, the structure is different. The singularity is a ring, not a point or a surface, and the structure of the spacetime inside contains regions where closed, time-like curves exist. Geodesics, paths through spacetime, can circle around the ring singularity and come back to the same point in spacetime, traveling backward in time in the process. The Kerr solution, taken at face value, contains time travel. Now, whether this time travel in the Kerr interior is physically real or a mathematical artifact is debated. The interior structure of the Kerr solution is probably not stable to small perturbations. Real rotating black holes formed from the collapse of matter may not have the same interior structure as the idealized eternal Kerr solution. And, as Hawking's conjecture suggests, quantum effects may prevent the closed time-like curves from forming. But the mathematics of the Kerr solution is suggestive. There is another exotic scenario for time travel in general relativity involving objects called cosmic strings. Cosmic strings, if they exist, are hypothetical, one-dimensional topological defects in the fabric of spacetime, left over from phase transitions in the very early universe. They would be extraordinarily thin, perhaps thinner than an atomic nucleus, but could extend across enormous distances, even cosmological distances. In 1991, the Princeton physicist J. Richard Gott showed that two cosmic strings moving past each other at high velocity would create a space-time geometry in which closed, time-like curves could form. The geometry of two rapidly moving strings creates a kind of loop in space-time that allows world lines to circle and return to their starting point in both space and time. Gott's cosmic string time machine was taken seriously enough to be published in physical review letters, and it generated considerable discussion. However, Gott's mechanism has problems. The total energy of the cosmic strings required to create the time machine would have to be comparable to the mass energy of half the observable universe. This is not a practical limitation, but a fundamental one. The universe doesn't appear to contain cosmic strings of the right type, and even if it did, creating a time machine from them would require an impossible concentration of energy. The general lesson from wormholes, Kerr black holes, and cosmic strings is that general relativity, pushed to its extremes, seems to allow time travel to the past in principle. But every specific mechanism requires something impractical or forbidden by quantum mechanics or other constraints. The universe seems to conspire to keep time machines theoretical. Let me also tell you about something that sounds like time travel, but is a more modest and real phenomenon: the way that memories and records of the past persist. In a real sense, the past leaves traces in the present. The universe has a memory. It keeps records. Every physical process leaves effects that encode information about what happened before. Your memory is a record of your past. A photograph is a record of a moment. A fossil is a record of an ancient organism. A geological stratum is a record of a period in Earth's history. The cosmic microwave background is a record of the universe when it was 400,000 years old. Gravitational waves from a neutron star merger carry the record of that event billions of light years across space and billions of years through time. In this sense, accessing the past is not impossible. We do it all the time by reading these records. Archaeologists access the human past through the artifacts left behind. Paleontologists access the deep past of life through fossils. Cosmologists access the deep past of the universe through ancient light and gravitational waves. We don't travel to the past, but we access information about the past through its traces in the present. What makes time travel in the dramatic science fiction sense different is that it involves physically being present in the past, interacting with it, potentially changing it. And that is the part that either requires exotic physics, violates the laws of causality, or requires the self-consistency of Novikov's principle, or branches into parallel timelines. Before we get to the close of our journey tonight, let me tell you about one more aspect of time that is entirely personal and subjective, but that deserves space in any complete discussion: the way we perceive time. Human beings are notoriously unreliable at estimating time accurately. We have no direct sensory organ for time, the way we have eyes for light or ears for sound. We infer the passage of time from bodily cues, environmental cues, and the counting of events and changes. The result is highly variable and context-dependent. Time seems to pass more quickly when we're absorbed in something interesting. The hours fly when you're doing something you love. Time seems to pass more slowly when we're bored or anxious or in pain. Waiting for a delayed train or sitting in a dentist's chair, minutes can feel like hours. High-stakes situations, moments of fear or danger or intense excitement, are famously perceived in slow motion. People who have survived accidents often report that time seemed to slow dramatically, allowing them to perceive details they wouldn't normally notice. This slow motion effect under stress seems to be a feature of memory reconstruction rather than actual perceptual slowing. The brain processes an extraordinary amount of information during high-stakes moments and then encodes the experience as having taken longer because more details were captured and stored. Time didn't actually slow for the person, but the density of their memory of the experience makes it feel that way in retrospect. There's also the well-known phenomenon of time seeming to accelerate as we age. A year feels shorter at 50 than it did at 10. Various explanations have been proposed. One is proportional. A year at age 10 is 1/10 of your entire life, whereas at 50 it's 1/50th, so it represents a smaller fraction of your total experience and is compressed accordingly in memory. Another is novelty. Childhood is full of new experiences, and novel experiences are processed more richly and remembered more distinctly, making time seem fuller and slower. As we age, more of our experiences are routine, processed automatically without deep encoding, and the periods between memorable events seem compressed in retrospect. The philosopher and psychologist William James noticed this in the late 19th century. He wrote that the young may have the long years ahead, but the old have the longer life behind them already, and that as we age, the time seems to pack into less and less space in memory. His analysis, written in 1890, prefigures modern cognitive psychology's understanding of how memory and attention shape our experience of time. For thinking about time travel, all of this matters because it reminds us that our relationship with time is not purely physical. It has psychological, neurological, and experiential dimensions that physics doesn't fully capture. The time travel that physics makes possible, relativistic journeys into the future, would involve the traveler experiencing normal subjective time passing, with no inner sense of accelerating forward. Only the comparison to others, to the Earth that aged faster, reveals the time travel. The physics is in the space-time geometry. The experience is in the mind. And the time travel we most often imagine, going back to a moment in our own past, is perhaps most fundamentally a psychological experience. The memory of a moment, the wish to be there again, the sense when we think of someone we've lost that they are somehow still accessible if only we could find the right path back. This is not physics, but it's the reason time travel matters to us, why we've been telling stories about it since H.G. Wells sat down to write his novel in 1895, why the question of whether the past still exists in the block universe feels not like a technical point in physics, but like something that matters personally. If the past still exists, in the block, at its location in space-time, then the people we've loved who are gone are still there, at their location, still experiencing their lives, still laughing, or talking, or just being present in whatever moment you remember most vividly. Not gone in the sense of ceased to exist, just elsewhere in time, the way someone in a distant city is not gone, just elsewhere in space. That's what the block universe offers, if it's true. Not the ability to go back, but the permanence of what was. The assurance that the past is not erased, that every moment that happened continues to have happened, permanently, as a feature of the four-dimensional structure of the universe, including the moment you thought of at the beginning of tonight. What would be disorienting is the arrival. Coming out of the wormhole to find yourself in a different time, surrounded by different people, with different technology and culture and landscape. The science fiction tradition spends enormous energy on the question of how you know when you are, and that's the right instinct. Time travel, if it were possible, would be less about the journey and more about the landing. Less about the physics of the mechanism and more about the shock of context. A traveler, arriving in the past from our present, would be carrying an enormous amount of knowledge about events that hadn't happened yet. They would know about technology that didn't exist yet. They would understand science that hadn't been discovered. They would have memories of a future that the people around them couldn't yet imagine. They would be, in the most complete sense, a stranger, not just from another place, but from another context, another world of knowledge and expectation and reference. This is actually one of the more interesting things to think about in the context of time travel, not whether it's physically possible, but what it would mean culturally and psychologically to be displaced in time. The time traveler to the past would have no one to talk to who understood their frame of reference. Everything that seemed normal to them would seem bizarre or inexplicable or impossible to the people around them, and everything that seemed normal to the people of the past would seem alien and constrained and limited to the traveler from the future. And the traveler to the future faces the mirror version, arriving in the far future, knowing nothing about what has happened in the intervening years, understanding nothing of the technology or the culture or the history that the future people take for granted, being the one who is behind, not ahead, being the one who seems limited and constrained, being the stranger who needs to be helped and explained to, rather than the one with superior knowledge. These asymmetries are part of what makes time travel stories rich when they're told well. Not just the physics and the paradoxes, but the human dimension of temporal displacement. For thinking about time travel, this matters because it suggests that even if you could travel in time, your subjective experience of the journey would be unremarkable. Relativistic time dilation is gradual and continuous. You don't feel it happening. If you went on a fast relativistic journey, you would simply experience normal time passing and would arrive to find more time had elapsed for everyone else. The exotic physics would be in the spacetime geometry, not in your felt experience of the journey. What would be extraordinary and disorienting would be the arrival. Let me also briefly talk about how time travel in science fiction relates to the physics, because I think it's worth being honest about where fiction and physics align and where they diverge. The most common form of time travel in fiction is the kind that goes backward in time and allows the traveler to change history. Back to the Future, the Terminator films, Doctor Who, Groundhog Day, Avengers, Endgame. All of these depend on the ability to go back and change something, with consequences for the future. This is the most dramatically interesting form of time travel, because it allows for tension and choice and consequence. Physics, as we've discussed, has nothing definite to say about whether this is possible. General relativity permits it in principle, in certain exotic spacetimes. Quantum mechanics may prevent it through the chronology protection conjecture. The grandfather paradox either constrains what you can do in the past, as Novikov suggests, or sends you into a parallel timeline, as many worlds suggests, or allows for quantum-consistent loops, as Deutsch suggests. None of these possibilities is ruled out. None is confirmed. The one thing physics does say fairly clearly is that if past-directed time travel is possible, It would require exotic conditions, exotic matter, enormous energies, or geometries of space-time that don't naturally exist in our neighborhood of the universe. It would not be achieved by a Victorian gentleman building a contraption in his laboratory, nor by accelerating a DeLorean to 88 miles per hour. The energy scales and geometric conditions required are at the level of the very early universe or the vicinity of black holes, not the level of engineering projects. Future-directed time travel, on the other hand, is exactly what physics predicts and confirms. And science fiction is generally right about this too, though it often focuses on the paradoxes of the past. Interstellar handles it with real care, as Kip Thorne ensured. The Martian, though not about time travel, captures the reality of relativistic communication delays. And there are scattered examples across science fiction of stories that take the confirmed, one-way, future-directed time dilation seriously, treating it as a tragedy of displacement rather than an adventure of history-changing. The displacement aspect is worth dwelling on. If you traveled to the future via relativistic motion and returned, you would find yourself in a world where everyone you knew had aged or died, where technology had moved on, where your cultural references were a century out of date, where you were effectively a stranger in your own home era. No paradoxes, no grandfather to threaten, just the loneliness of having moved forward while everyone you loved moved forward at a different rate and arrived at a different place. That's the confirmed form of time travel. It's real, and it's quietly devastating to think about. The astronauts who spend long periods on the ISS return to a world that has aged a few milliseconds more than they have. It's imperceptible, but the principle is the same as the traveler who returns from a relativistic journey to find a century has passed. Degree, not kind. Now let me also briefly mention something that often comes up in discussions of time travel. The question of whether the universe has a preferred direction of time at the quantum level, and whether this has implications for backward time travel. At the microscopic level, as we discussed in the Arrow of Time section, physics is mostly time-symmetric. The equations look the same running forward or backward, with one exception: the weak nuclear force through the CP violation we discussed in the antimatter conversation treats the past and future slightly differently. The violation is tiny, but it's there. Does this tiny asymmetry in the fundamental laws, this slight preference of the weak force for one direction of time over the other, provide a fundamental obstacle to backward time travel? Almost certainly not directly. The CP violation is too small and too specific to be the mechanism that prevents time machines. But it's suggestive. It suggests that the universe's asymmetry between past and future runs deeper than just thermodynamics and entropy. It's present even at the level of elementary particle interactions. The universe, at its most fundamental, may have a preference for one direction. That preference is expressed most dramatically in the thermodynamic arrow, in the relentless increase of entropy that drives us from the low entropy past to the high entropy future. And it may be reinforced at the quantum gravity level by whatever mechanism underlies the chronology protection conjecture. Together, these might constitute a genuine, deep physical prohibition on returning to the past. Or they might not. The physics, as I've said, is genuinely uncertain. What we know for certain is this: right now, you are moving forward through time, 1 second per second, in the only direction available to you, accumulating experience and memory and the weight of history, heading toward a future that is either already fixed or genuinely open. You cannot go back, but everything that was real, and everything that will be is coming. That's enough for tonight. But before I let the night fully take over, let me just say one more thing about the way the past persists. The universe doesn't forget. Every event that has ever happened has left traces in the present state of things. The Big Bang left the cosmic microwave background, that faint glow of ancient light that fills the entire sky. The first stars left the chemical elements that compose us, forged in stellar cores before the sun existed. Every stellar explosion scattered its products into space. Every collision of objects left gravitational wave signals rippling through space-time. Every living thing that has ever existed has left biological or geological or chemical traces that persist long after the organism is gone. Every human being who has ever lived has left some trace in the world, however small. A word written somewhere, a child, a change made to something that changed something else, an influence on one person who influenced another. And you, right now, in this moment, are making a trace. You are leaving evidence that this night happened. The neurons firing in your brain are creating memories that will persist. The breath in and out is mixing with the air in the room in a way that will diffuse and spread and eventually reach the atmosphere. The warmth of your body is radiating outward. You are leaving your mark on the present state of the universe, in ways too small to measure individually, but real in aggregate. This is what it means to exist in time, to leave traces, to be the cause of effects that persist after the cause is gone, to add to the long accumulation of history that the universe carries forward, encoding in its present state everything that has led up to it. When you look at the night sky, you are reading that history. When you look at a rock stratum, you are reading that history. When you look at your own body, made of atoms forged in stellar cores before the sun existed, you are the history of the universe, embodied and walking around. In that sense, we are surrounded by the past at all times. We are made of the past. We carry it with us. We are it. Time travel, in this deeper sense, is not something that requires exotic physics. We are already time travelers in the most fundamental way. We are the continuation of everything that came before, the living accumulation of 13.8 billion years of cosmic history. Let me slow down now and come back to where we started. That moment you thought of at the beginning, the afternoon you'd go back to, the conversation you'd have again, the person you'd see once more. You can't go there. Nothing in the physics we've discussed, not wormholes, not relativistic time dilation, not self-consistent time loops, offers a practical path to that kind of return. Physics can take you into the future, but going back to your own past, to the specific moments in your own life that you carry with you, is not something any known or theorized mechanism allows. But here's the thing. That moment is not gone. In the block universe view, it still exists, as real as this moment. Every good moment you've ever lived is still out there in the four-dimensional structure of spacetime, at its location in time, exactly as vivid as it was when you lived it. The universe has not deleted it. It has not ceased to be. It is simply at a different location in time than you are right now. Whether that's a comfort or a torment depends on your temperament. Some people find the block universe deeply consoling. Every moment that was good is still there, permanent, unchangeable, as real as anything. The afternoon in question, with whoever it contained, whatever light was in it, whatever was said or felt, is still at its location in the block. It is not erased. It is not less real than today. It is simply elsewhere in time, the way a city is elsewhere in space when you're not in it. You are not there, but it is there. Others find the block universe disturbing. If the future already exists, fully determined, in what sense are we free? In what sense do our choices matter? If everything that will happen is already there in the block, the feeling of making a decision, of choosing one path over another, seems to be an illusion. We're just moving through a predetermined structure, experiencing it sequentially, feeling as if we're choosing when the choices are already made. Philosophers have argued about this for centuries, and the answers depend partly on how you define free will. One influential view is compatibilism, the idea that free will and determinism are compatible, that what matters for freedom is not whether the future is determined, but whether your actions flow from your own reasons and desires rather than from external compulsion. A determined universe in which you act according to your own values and reasoning is, on this view, a universe in which you are free, even if your choices were always going to be what they are. The block universe doesn't necessarily threaten this kind of freedom, and the memories you have of those moments are real physical traces of the past, encoded in the patterns of neurons in your brain, which are themselves made of atoms that have been here since the Big Bang. Your memories are the universe's way of keeping a record of what happened to you. They are the past, persisting into the present, the way fossils persist, the way the light of distant stars persists, the way the cosmic microwave background persists. You are not separated from your past. You are made of it. Every experience you've ever had has changed you, subtly or dramatically, and those changes are still here, in you, right now. The past is not somewhere else. It is in you. That's the deepest thing about time, maybe. Not the wormholes or the paradoxes or the self-consistency principles, but the simple fact that the past accumulates in us. We carry our histories. We are made of our histories. And the people and moments and afternoons we love don't vanish. They become part of the structure of who we are, permanently, irreversibly, in a way that no passage of time can undo. Let that settle now. Let the paradoxes drift away. Let the wormholes and closed time-like curves and the chronology protection conjecture all blur into the background, interesting as they are. What stays is simpler. Time is strange. Physics has shown us that it is stranger than Newton imagined, more elastic, more relative, more tied up with space and gravity than anyone thought. Traveling into the future is real. Gravitational time dilation is real and being corrected for in every GPS calculation. Time passes differently depending on where you are and how fast you're moving. The block universe may mean the past still exists, as real as the present. And through all of this strangeness, the moments we've lived are not erased. The physics of entropy and thermodynamics has driven us from those moments into this one, and onward, and the direction of that journey is fixed. But the moments remain, in the block, in our memories, in the physical effects they left on the world and on us. Let me sum up the whole landscape one more time, slowly, one last time, so it can settle into you before you sleep. We are traveling into the future right now, at the rate of 1 second per second. This is baseline time travel, available to everyone, requiring no exotic physics. We can increase our rate of travel into the future by moving fast or by spending time in stronger gravity. The Scott Kelly twins demonstrated this at a human scale. Muons raining down from the upper atmosphere demonstrate it every second. GPS satellites require relativistic corrections every day. All of this is confirmed, measured, real. At relativistic speeds close to the speed of light, the effect becomes dramatic. A hypothetical astronaut traveling at 99% of the speed of light for 10 years of their own experience would arrive back on Earth to find 700 years had passed. They would be a genuine time traveler, displaced into Earth's far future, separated from everyone they knew by centuries of earthly history. For traveling into the past, physics has no confirmed mechanism. General relativity allows, in principle, for traversable wormholes, for certain features of the Kerr black hole interior, for cosmic string configurations that permit closed time-like curves. But all of these require exotic matter, or are unstable, or are ruled out at the quantum level by arguments like the chronology protection conjecture. The grandfather paradox and related paradoxes of past-directed time travel remain unresolved. The Novikov self-consistency principle, the many worlds resolution, the Deutsch quantum resolution, each offers ways out, but none is accepted as definitive. The physics of time travel to the past remains genuinely open. The nature of time itself is not fully understood. The block universe, presentism, and emergent time views all have serious supporters. The arrow of time traces to thermodynamics. The experience of time flowing may be a feature of consciousness rather than of physics. What time is, at the deepest level, is one of the great open questions in all of human inquiry. You've spent some time tonight with all of this, and now I think it's time to let it go. Think about the moment you started with, the one you'd go back to. Let it be there, in the block, at its location in time, as real as anything else. Let it be in you, as the trace it left, as the way it changed you, as part of the structure that makes you who you are tonight. And let this moment be too. This moment of slowing thoughts and deepening breath, and the quiet of wherever you are. This is building in you right now. It is accumulating. By tomorrow it will be in your past, and by next year it will be in your distant past, but it will still be there, in the block and in you. You cannot go back. The thermodynamic arrow points one way only, for any macroscopic system. The entropy will not decrease. The wormholes are theoretical. The chronology protection conjecture stands. But you can go forward. You always have. 1 second per second, through time, carrying everything that has happened before, heading into a future that is either already there in the block, or is genuinely open, depending on which view of time turns out to be right. Either way, it arrives. The future always arrives. Morning comes. The next moment happens. Time moves on whether we're watching or not, whether we understand it or not, whether we've solved the grandfather paradox or not. And right now, the most productive thing you can do with time is to give some of it to sleep, to let the clock of your consciousness slow, to let the day be behind you, and the night around you, and the thoughts dissolve into the particular quiet that precedes sleep. The past is in you, the future is coming, and the present, this narrow moving knife edge that Augustine described, this is where you are, right now, and it is enough. Let your body be heavy. Let the physics of time travel, real and hypothetical, confirmed and conjectured, philosophical and mathematical, let it all drift the way all thoughts drift when sleep comes. The wormholes can hold their shapes without you watching. The grandfather paradox can remain unresolved without your assistance. The block universe can be all 4 dimensions without you keeping it organized. You are a small, warm thing in a large universe, where time does strange things. The universe is much older than you, and will be much older still. It has been here for 13.8 billion years before you arrived, and will be here for an almost inconceivable time after you depart. And in all that time, in all those billions of years. You are here, right now, in this small, specific moment, with your specific history, and your specific memories, and your specific body, in your specific place. Sleep is its own kind of time travel. You close your eyes, and when you open them, hours have passed, in an experience that felt like nothing. You will wake up in your own future, a small journey forward, unremarkable by the standards of what physics permits, but real in the way all time travel is real, a movement forward through the block, from this moment to the next. Sleep is its own kind of time travel. You close your eyes, and when you open them, hours have passed, in an experience that felt like nothing. You will wake up in your own future, a small journey forward, unremarkable by the standards of what physics permits, but real in the way all time travel is real, a movement forward through the block, from this moment to the next. Sleep is also, in a small way, a release from time. During sleep, you are not tracking the passage of seconds. You are not experiencing the now, moving into the future. You are simply absent from the stream of conscious temporal experience, and then present again, several hours forward. You step out and step back in, and the universe has moved on without you noticing. This is one of the most ordinary, extraordinary things that happens every night to every person who sleeps. The subjective experience of several hours compressed into nothing. A small, daily, mild version of the relativistic time traveler who goes very fast and returns to find more time has passed than they experienced. Not the same physics, but the same human experience of non-continuous time, of gaps in the sequence, of being pulled forward without awareness of the journey. Sleep well. Time will do what it always does. It will pass, in the only direction it goes for us, from this moment to the next, carrying you forward, as it carries everything forward, into whatever comes next. The past is not gone, and the future is not yet here, and right now you can sleep. Rest well. The present moment always will have been. Sleep well.